Yay!
Yay! Okay, let's go through a non-trivial, simple circuit that's got parallel and series components, and let's see what the current through each thing and the power dissipated by each resistor is. All right, so I got this little network. The voltage source is 80 volts. I've got resistors A, B, C, D, E, and then I wrote their resistances in yellow just so we could kind of pick them out easier because all the writing, it's hard to pick them out. So let's see, if these are all light bulbs, let's say, let's find out the current through each bulb, the voltage across each bulb, the voltage dropped across each bulb, and then how bright each of them are. Let's find their powers. So sometimes in class I'll call this like VIP. We're going to find voltage, current, and power through each of these. Okay, the first step, always, we do the same thing. It's the same recipe every single time. So the first step always, oh, that's terrible. I'm not going to call it step A because I have resistor A. Anyway, the first step always is to find the equivalent resistance of the entire circuit. The reason for that is because that's what the battery sees, right? The battery is, in some sense, trying to push charge around this network, and the battery just sees some total resistance. It has no idea how the resistors are all arranged. It just knows that there's some total resistance to pushing the charges around. So that's what we're going to try to find. It's like collapsing all the resistors down to one equivalent resistor, and that's what's fighting the battery. So, okay, let's see. I've got A is in series with that parallel group, CDE, and that's in series with B, and then it goes back to the battery, right? So my equivalent resistance is just going to be the resistance of A, 5, plus the resistance of that parallel group. So the parallel group, I'm going to do 1 over 20 plus 1 over 10 plus 1 over 20, and then I got to remember to flip it. And then I got my 10, and that's it. So that will collapse everything to one resistor. All right, look at that parallel group. A 20th plus another 20th, that's 2 20ths. 1/10 is another 2 20ths. So that looks like 4 20ths. That's a fifth. Right? And then when I flip a fifth, I get 5. So this whole thing becomes 5. So 5 and 5 and 10. The equivalent resistance of the whole network is 20 ohms. That's what the battery sees, right? The battery has no idea how they're actually arranged. It just knows that there's a total of 20 ohms of resistance. The reason I need that is because the very next thing we always want to figure out is the current coming out of the battery. So the current coming out of the battery is just the voltage of the battery divided by the amount of resistance that the battery sees, REQ. So that's just going to be 80 divided by 20 for 4 amps. There we go. So I got 4 amps coming out of the battery. And then it's useful now to keep in mind, who sees 4 amps? Well, all those 4 amps have to go through A, and then all the 4 amps have to go through B. That's one of the principles, is that we don't lose current going around a circuit. It can branch, like when we go through the parallel branch, the current can split, right? But then it all has to join back up. So what we're going to find is that when you get here, the current splits 3 ways, but then it joins back up. And all the current, all 4 amps, goes through B. So what we know is IA, keep a little running tab, IA equals 4 amps, IB is 4 amps. I don't know what I, C, D, and E yet, but we'll figure it out. And so what you do is you just sort of work your way around a circuit. There's no more complicated formulas than we're just going to use that Ohm's law, V equals IR, and just a couple of principles as we work our way around a circuit. Okay, well, if I know the current through A, and I know the resistance of A, then I can find out the voltage dropped through A. all right? Because here's another one of our principles, and that is the battery gives these charges 80 volts worth of energy, all right? That's not technically correct, is it? Because voltage is energy per unit charge, but all these charges are the same. They're all like, well, they're positive, right? But we know that's sort of a fiction, a conventional current. They're really electrons going the other way, but we know that. But just with loose language, I'm going to say the battery is giving them 80 volts worth of energy. And by the time they come back to the battery, they have to have used all the energy up. So remember, that's one of the principles, is that we don't use up current as we go around the circuit, we use up energy as we go through the circuit. And that kind of makes sense, right? You don't lose electrons. If 100 electrons come out, 100 electrons better go back, or else something is getting charged. So instead, the same number of electrons have to come back, but they do lose energy, and it's the energy you get from a glowing light bulb. So if the battery gives them 80 volts going out, they have to lose 80 volts going around the circuit. Well, they're going to lose some going through A because the light bulb at A is going to glow. So how much voltage do we lose, do the charges lose? How much energy, loosely speaking, do they lose going across A? Well, we can figure that out. VA is just IARA. Right? Ohm's law ought to work for each individual component. So what's the current through A? It's going to be 4. The resistance is 5. And so we get 20 volts. So these charges lose 20 volts as they go across A. What about CDE? Okay, now here's a trap. Here's what a lot of students do the first time they see it. CDE are in parallel, right? And the way that I've even drawn it is that it looks like they're sort of in parallel with the battery. And so initially you might say, oh, the voltage drop across C, D, and E are 80 volts because they're all in parallel. And resistors in parallel all have the same voltage drop. And it looks like they're in parallel with the battery, so they each have a voltage drop of 80 volts. But that's a trap. It's not true, because what if they did? A given charge will go through either C or D or E. And if it drops 80 volts there, it can't drop anything over A and B, right, on the way back to the battery. So that can't be it. What we have to do is we have to figure out the drop over A, and then we have to figure out the drop over B, and whatever's left over, that must be what's dropped over CDE, because the total has to be 0. Right? So since we figured out the voltage drop across A, now we have to do B. The voltage drop across B is IBRB. So that's going to be 4 amps. And what is it? 10 ohms. So we do 40 volts. We drop 40 volts across B. So again, let's go through the logic. A charge comes out of the battery with 80 volts. After going through A, it drops 20. So now it's got 60 volts worth of energy, right? And then it drops some amount over CDE. And then after going through B, it'll drop another 40. And that better be 0. And then it better be 0, right? Because it goes back to the battery with 0. So now we know what the voltage drop across CDE is. This implies the drop across C and D, we know they're all equal because they're in parallel, but now we know what it is. It's got to be 20 volts, right? Because that's what's left over. So imagine a little charge coming out, well, 80 volts, right? Maybe I'll make it red. So imagine a little charge coming out from the battery. It goes through A and drops 20. So now it's going to have 60. So now it comes here, and let's say it goes through E. It's got to go through one of them, only one of them, right? Goes through E, it has to drop 20. So now it's got 40 volts left. And now it goes through B, and we already know it drops the other 40. That goes back to 0. So it works. So the total amount of voltage dropped has to be 80, which tells us, now that we know what A and B are, that tells us what the drop across CDE have to be. Okay, 20 volts. Well, now we're all set, because if we know the voltage drop across those resistors, now we can figure out the current through those resistors, because that's something we didn't quite know. The current across C is just going to be the voltage of C divided by the resistance of C, right? So the voltage is 20. The resistance of C is 20. So this means that this is 1 amp. ID is VD over RD. Let's see, so that's going to be 20 divided by 10, so that's 2 amps. And then, can I fit this above my head? Yep. IE is VE over RE. Let's see, it's 20 volts again. Each of them are 20 because they're in parallel, and it's 20 ohms. And so this is going to be 1 amp. Look how cool that is. Okay, remember that we had 4 amps. 4 amps were coming down this branch, right? Oh, I already drew that in white. I'm not going to confuse it. Okay, we got 4 amps coming through A, and it hits this junction right here. That would be a junction, right? We got 4 coming in there. And now look what this says. This says C gets 1, and then D gets 2, and then E gets 1. So it splits 3 ways, but it splits 3 ways, of course, so that the total is 4, right? We don't lose any current. So 1, 2, 1. And look, that's in the same ratio as those resistances. And it makes total sense. You get more current where there's the least resistance down through that middle branch, right? Twice as much because the resistance is only half as much. And then when they come back here, you get 1, 2, and 1 coming back, giving you 4 down here at this junction. Okay, what's cool is when you do circuits problems, often there's a way to see if you're right. So one way to see if you're right is make sure at these junctions, go back and just check that all these currents sort of add together. You're not losing any current at the junctions. It should all make sense. Okay, so we know the voltage drop across all of these resistors. We know the current through all the resistors. So now let's just get the power. Power of A, B, C, D, and E. Power is I squared R. I squared A, R, A. Let's see. So the current is 4, so it's going to be 16 times 5, or 80. Looks like 80 watts. Power B, it's going to be 4 squared 16 times 10, or 160 watts. Power C. Power C is going to be, who did C? C got 1 amp, so squaring 1, you get 1, times R, 20. So this is going to be 20 watts. Power D, it's going to be 2, so I square it, 4 times 10, 40 watts. And then how bright is E? If that's a light bulb, I get 1 squared is 1 times 20, 20 watts. So who's the brightest light bulb? The brightest light bulb, kind of by far, is going to be B, right? Ooh, here's another way you can check your answer. Let's check to make sure everything is okay. If I add together the brightness of all these bulbs, I should get the same amount of energy per second, the same wattage as what the battery is pumping out, right? Because we're in energy conservation. We shouldn't be losing any energy anywhere. So if I add together all of these powers, what do I get? 80 plus 160, what is that? 240 plus 20, 260, 300, 320. So I should get 320 watts total through all the resistors. And how do we check to make sure this is okay? This better be equal to the power supplied by the battery. How do we check that? The power supplied by the battery, oh gosh, I'll just use little b for battery. Hopefully that's not confusing. Is just going to be the current coming out of the battery times the voltage of the battery, right? It's just IV for the battery. And so that's going to be 4 times 80, and take a look at that. What do we get? 320 watts. Check. Okay, so it looks like we've probably done everything right. So that's the nice thing on a lot of these problems, is that you can check. You'll be able to make sure that you did all the arithmetic right, because it's easy to transpose one of the resistances or use the wrong number or something. But this is a way that you can check and see that you're right. All those powers add up, so energy is conserved. All the currents add up at the junctions, so we're okay. And that's it. So just by repeating Ohm's law all the way around the circuit, and then the principles of losing all the voltage as you go around a loop, and conserving current at the junctions, just by invoking all of those principles, you can sort of detective your way around a circuit and figure it all out. That's really cool.